or you just go to bed tonight? Then
I had myself mute. I was talking probably. But in the first 5 minutes of the class, probably you do not hear me because I forgot to unmute myself. If you go to back to watch the recording, you do not hear me for the first 2 minutes. Now, okay, now on the screen share, this is going to be the overall map of what we are going to do. Today we are in week 2. We are just going to head strong go for week 15, and that's going to be the roadmap. Each week, we are going to cover 1 or 2 functional groups, okay? Then by the end of the term, you see that everything is completed. Now, before we just move on to work actually with the functional groups, I want to, let's ask, because some of you come from the pharmaceutical sciences in this class, or pharmacy. Anyone from the pharmacy background? Oh, champions. Look at that. Now, you come from some very good knowledge of the pharmaceutical sciences. And the question which I have for the all class is this. Why do we call them a functional group? The functional, what does it signify there? For example, if you look at that, for example, you look at the alcohol. If you locate the functional group, alcohol there, for example, this one, which is there, it comes with the R. R means the hydrocarbon bearing structures. Guys, please quiet. It means that the hydrocarbon bearing structures, whenever you see R, it means that you can think of a subway, for example, the subway that you take from your home to come to the college, but each wagon there is a carbon, nothing else. R means a carbon bearing structure, if you see in these symbols there. But when we look at, for example, of one of the functional group, as an example, that this is called alcohol, you see that we have the R. We are so lazy, we are not going to write C, 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 something like that, the train of the carbons. We are so lazy. We put R. R means everything comes as a carbon. And the thing which is significant there is the presence of the hydroxyl group, which is OH or OH. Okay. And the question is that, for example, that becomes one very important functional groups that you're going to see that it's going to be a dominant functional groups all the way to week 15. But we ask ourselves, what is the significance? Or for example, carboxylic acid group. For example, if you go to the middle line, which they have the circle which is in green, you see that, for example, we have carboxylic acid group. It is also a very dominant functional groups that we work with them. And also, if we just do the biochemistry, which most of you have done, you see that this is a very significant functional groups because it's a part of the terminus of the amino acids and the protein as a peptide structures. Then now, the question which we ask ourselves is that, why do we care about the functional groups? Why? Why do we have to classify them? The first question. And what do they mean? Why do we need to know which functional group we are working with? And that's an important question that I have. We have two champions here. They come from the pharmacy background. They may know the answer right now, but I want everyone thinks of it because everyone had an organic chemistry probably before in degrees that you had. Then what is the significance? Huh? Yeah, please. Characteristic of chemicals, or better to say reactivity. What does it mean? For example, imagine that, guys, you take the subway to come to the class, huh? Yes? No, you do not take it. Sometimes you have taken the subway here. Sometimes you see when you take the subway in Toronto, we said that the train, which, for example, you're moving all the way to Union Station, it becomes the hydrocarbon bearing structures. But you see, when you, for example, after 4, 5 p.m., you take the subway, you see something very interesting. Nobody's talking to anyone. People are so depressed, are so exhausted. They don't want to look at anyone. Have you seen that in Toronto? People, it seems that everyone is dragging themselves. It is actually the case of the hydrocarbon bearing structures. Nothing interesting goes on there. But imagine that. But have you seen sometime that you take the subway by around, for example, you take the subway before 11 or after 11 p.m. on Saturday night? Have you taken that? 11 p.m. Sunday, you go towards downtown, you pass King Street, go before the Union. You see that? No. There are some people who seemingly are drunk. Some of them comes in the train, it starts yelling. Have you seen that? It happens a lot during the Saturday. You see that you look at them in a very, oh my God, we are scared of them. But they are joy of the life in Subway because they make everything seems exciting. That's the issue of the functional groups. If you have a Subway without those people who are drunk and yell at the Subway, this is the issue of the regular hydrocarbon structures. Nothing interesting happens with them. No reactivity. But when you add, for example, a hydroxyl group there, like the OH, or carboxylic acid, which it comes with the double bonding with the O and the hydroxyl group, it acts like those drunk people in the subway, that they attract attention, okay? And they induce reactivity. Then all the things which you see that, all the excitement of the organic chemistry comes just because of these functional groups, like the hydroxyl. Otherwise, for example, look at the first row from the top, the alcohol, which is ROH. If you remove the OH, just the R, I guarantee nothing significant is going to happen. It becomes a boring subway after 5 p.m. in the, let's say, Monday. Monday, take the subway. After 5 p.m., you see you're falling dead because everyone seems so depressed. You say, oh my God, what a town is this? And now it becomes like that. Then as a result, these functional groups that we're going to learn, they are just giving some excitement to the structure. It makes them reactive. If you have, for example, imagine yourself, you are sitting in a subway with someone, for example, some people, they do not love some professions. For example, I have a friend who doesn't love to be an accountant. Then when he's done with the job, after 5 p.m., he wants to kill himself. You sit next to him in a subway, you do anything, he doesn't even talk to you. Okay? But if you, for example, you have a hydrocarbon bearing structures, whatever you do, nothing is happening with them. No reactivity, no reaction, nothing new happens with them. But as soon as you give the hydroxyl group to them as a functional group, they become highly reactive. They become talkative in a sense. If someone is sitting next to you in a subway and he wants to talk to you about everything, they become very reactive. And that's actually what we need in organic chemistry. Because the purpose of the organic chemistry that we're just going to do, and I'm going to align it towards a drug design, which you use organic chemistry in order to synthesize a new chemical compounds that along the way they have some therapeutic effects. It becomes a little bit complicated because you have to talk about the affinity, about the selectivity. We don't go that much far, but we just guide our lectures towards the drug design. That it means that you become interested in the organic compounds with very specific characteristic functional groups that they can react. By reaction, I mean socialize with the other functional groups of the other chemical compounds. Then in that sense, that's what we expect in organic chemistry. We have to make everything to come into discussion. Let me just close the door because the other class have some kind of fun time. Now, that's actually what I meant. Then from next week, and actually from today, all the thing that we do, we have to always search for this functional group. And for example, the second half of the class that we have, I'm just going to give you the structure of a drug like acetaminophen or aspirin. Then you have to search for the functional groups in there to identify as many as you can. Because each functional group in a chemical compound has a lot to say. It seems, you look at, when after this class, you look at the chemical structures, when you look at them, it seems as if you hear a song. Actually, they are talking to you. They are talking to you with various different kind of a language because these functional groups, that's all we care about. Now, this map which we have over there, it's going to be on the Google Classroom today. And every week when we come back to the class, we focus on one. But why do we focus on one? For example, why? Probably we are just going to start in week 4 with the alcohols, with the hydroxyl group. Then why do we have to spend the whole 3 hours on the alcohols? Because as an overall rule, each functional group, it means that it makes organic chemistry so exciting. It brings something to the table to talk to you about. It's not a depressed guy because hydrocarbon bearing is a depressed guy. He doesn't talk to you. With the functional groups, they talk to you. That's important to see to who to talk to. You look at the compound, a drug, you see that maybe there are more than 7 functional groups at the same time on that drug. It means that this is something that you need to talk to. You cannot talk to anyone in the street. Do you go to talk to anyone in the street? No. You go to talk to selective people. Then now you see that if the functional group is there, is the time to talk to someone. But the way that you talk to me is different than the way you talk to your friend, then that's different than the way you talk to your parents. Am I right? Then we are going to learn each week the art and the specificity of how to talk to each individual functional groups because each functional group has a different style to talk with them. We're just going to see some common characteristic way how to talk with them. What is their reactivity? How do they react? Then anytime you see those functional groups in any structures, you know, oh, that's the way that I have to talk with them. And it's going to be unique with all functional groups. And that's why, first, we need to identify the functional group. Second, we have to see the details of their specificity. Each week, then we are just going to focus on them. Now, for today, any questions so far? No? Then you see from the top, today, we are just going to talk about of almost everything from the aldehyde to the ketones to the carboxylic acid to acid anhydride to ester to amide to acyl halide. You see, these ones are all important functional groups. But the ones that you're going to see that at the bottom one, they are just going to be not our priority. We are just going to focus on the first row and the second row. The one at the bottom, we do that if you have some time. Otherwise, we do not do that. Okay, and that's going to be the most important thing. Now, the second thing which I'm going to do, I'm just going to stop the share and use the whiteboard. Everyone sees the whiteboard? Yes. Awesome. Now, the other thing, now, today, I'm just going to draw you some very overall of the reactivity. The thing that you're going to see right now, do not panic because it is going to be very, very simple stuff, but the core concepts that we are just going to work. Guys, please quiet. Now, I'm just going to start today with the overall. I'm just going to talk today about the overall way that you just need to conduct the reactivity. Listen, the important thing in organic chemistry is that, and something that you will be assessed for both the midterm and final exam, because for the midterm and final exam, I'm not going to ask you about, for example, how to name your structure, because you learn how to name them after 2 weeks after the course, you just may forget them. Okay, I'm not going to ask this kind of stuff for the midterm and final exam. What you're going to be assessed is that I give you chemical compounds in either acidic or basic environment, then you have to complete the reaction. You have to do the pathways in order to find one or the collection of the products. Now, then we do not focus on one session how to name an alkane. No, we are not going to do that. We just focus only on the reaction pathways and reactivity. Now, I'm going to today show you one example. From next week, and we are just gonna build on it. Now, okay. Now, the first thing which I'm just gonna say is that the building blocks of organic compounds is carbon, okay? And the details about that, for example, about the electronegativity, those kind of stuff, I'm just going to teach it as we walk through the examples. Now, which say that, okay, the carbon is going to be R. Guys at the back, you two please come to the front. Come at the front. You over there, you over here. Over there, no, over there. Thanks. Now, what I said is that you see that the carbon is going to be the backbone of the organic compounds. Now, please do not do artistic stuff on the whiteboard. Now, you see that carbon comes with 2 hands and 2 legs. What do I mean by that? You remember from chemistry 1, the carbon has 4 electrons on its valence shell, and it means that it has a capacity and potential to just make bonds with 4 other elements. Then as a result, we call that it has 4 arms and 2 legs, 2 arms and 2 legs. Now, each one here, you see that it has a potential to be filled with some appropriate elements, depends on the environment. Once you can start to say that, okay, I'm just going to say, start with the basic one. Make the covalent bonds with the hydrogen. Okay? Methane, for example, that's the methane. We do not care what you call them, we more care about the reactivity. Now, sometimes you say, no, this is, for example, if I do these configurations, I have created a very stable, sometimes in the course, we have to jump into the thermodynamics because thermodynamics is so important. It's so important to understand the stability of the structure. You see that, for example, now I just made a very stable structures by adding 4 covalent bonds hydrogen to the carbon. But sometimes you say, no, I preferred instead of, for example, having the hydrogen there, add what? Add, for example, add 1, let's say, another carbon there. You see, this is still a very stable structures, huh? Because 2 hands and 2 feet of your central carbon, if I may call that, is fully occupied. However, you see that the other carbon who showed up there, you see every carbon comes with how many hands or feet? 4. Then it means that the one which we also have there, it should come with another leg and arm. You see, these two, this one, and this one. It means that it has the potential to be filled with one element. But you cannot bring any elements because there are many other considerations. But at this stage, if that's going to be the case, you say, okay, I have another carbon. I'm going to say, for example, I'm going to fill on this plate one hydrogen. I'm going to fill on this plate, for example, one hydrogen. You see, you are left with one. You say, let's give it another carbon because at this stage, I look at the hydrocarbon bearing structures. The name implies hydrogen and carbon. Then you see again here, you should come with what? 4. 2 arms, 2 legs. One arm is taken by the carbon over there. You are with what? 2, 3 empty plates to fill this. Now, I'm going to do this one. I'm going to say, I'm going to give this one hydrogen because hydrocarbon bearing structures, hydrogen and carbon becomes covalently bounded. The energy drops, becomes stable. I'm going to give this one hydrogen. However, for the other one which is there, I'm going to be a little bit picky. Why? Because I'm just going to give something different that we haven't done it yet. I'm going to remind you of the periodic table that you had it in chemistry 1. In the periodic table that we had in chemistry 1, you remember group 7, which we call that halogens. For example, if it was group 7, we had group 7. The first element was fluorine, chlorine, bromine, and iodine, right? Besides, this one becomes one, the radioactive elements. We do not work with that. Now, group 7, then I'm just going to pick one of these ones to just, instead of the hydrogen, I pick it there. Huh? Then I get this one, chlorine there. Why this is important? Because remember, we had to, from chemistry 1, it comes from group 7. If it comes from group 7, it means how many electrons do I have at the outer bound? Group 7 means 7 electrons. Then if 7 electrons comes, what is the octet rule? Because you remember, if, for example, imagine I put all the elements into my pockets. When I see you, I say hi, I drop you an element into this space. Can I do that? No, because remember, the elements can become stable if they are octet, means that they have 8 electrons in the outer bound. 8 electrons. With the group 7, I have 7 electrons in the outer bounds. Then if I draw a chlorine in the classroom right in front of you on the table, you should panic. Why? Because it becomes highly energetic and reactive. It's like, for example, have you worked with the TNT? You saw that in the movies, explosive materials. It's so dangerous. It's like the chlorine. It becomes so dangerous because the energy content there, it's so huge. You have to appease it, bring the energy down by giving 1 electron to the outer shell. And that's the covalent. And that's the purpose of making covalent bonds. Make the elements stable by giving the octet rule to them. Make the 8 electrons around them. Chlorine has 7 electrons. When it makes a bond with the carbon, it takes 1 electron covalently shared, then becomes 8. And that's why I can put the chlorine there. That's why you cannot bring everything in the plate. It has to be in a sense that it brings the octet rule. Now, then as a result, I synthesized in a very lazy way this hydrocarbon bearing structure, which we call that alkyl halide. We do not care what they are called, but it is one of the functional groups that we're going to work more with that next week. This is alkyl halide. Why halide? Because it comes from group 7. one of the things on the plates come from the halogen. That's why you call that alkyl halide. Now, I'm just gonna look at that, make it compact. I'm gonna look at the first carbon here. You see the first carbon comes with three hydrogen around it. I'm just gonna make it compact. I'm not gonna show two stretch arms, two stretch legs. I'm gonna compact it by CH3. I go to this carbon here. You see carbon comes with one hydrogen there, one hydrogen there, one hydrogen here. Becomes how much? Again, how many hydrogen this is around it? 1, 2, CH2. I moved from carbon to this. From this, I move over here. I see another carbon. I write it. How many hydrogen is around it? 2. What else am I missing over there? Chlorine or chloride. Then what to do with it? I'm just going to simply place it here. Huh? Chloropropyl. We do not care what you call this. But that's the thing that you see two structures. I have one expanded version, one compact version. This is a carbon-bearing structures that it has chlorine at the terminal. We call that alkyl halide. Okay? And that is becomes the foundation for the second half of the class. Now we're going to take a break. When we come back, I'm just going to walk you through where the reactivity of this structure happens. Next session is going to be the most important session for the next 15 weeks because I'm going to walk you through the secret of how to just start reactivity before we add many details of the solvents, of the polarity, those kind of stuff. Now, I'm just going to stop. When we come back from the break, we are just going to continue with this structure, but in a more elaborate way, how to find reactivity starts. Any question? Everyone's okay? Yes. Let me close it. Now, I'm just going to stop the recording. Yeah. Let me I hope you have put me on mute. Let me share the whiteboard.
Good morning.
Okay. The whiteboard. Okay. Now, please mute me on your system. Okay. Now, I'm just going to start from. Guys, please mute me. Jill, please mute yourself. Who is Jill? Jill. Okay. Now, I'm just going to start from where I just left before the break. From there, I'm just going to walk you through, just very simply, how we should start reactivity. Each week when we just start the session, we are building on this very fundamental thing. This is essential. This is the most important lecture that we are building right now. Everything from next week, it's an addition to this main thing that we are just going to talk. Remember, we just built very simple structure, chloropropyl, with the chloride here. Okay, that's what we finished. Huh? Oh, yes, everything should be CH2. CH2, CH2, Cl. what we did before we just went for the break. Thank you. Now, what I'm going to do is that I'm just going to expand it selectively at this point in order to show you something. I said that I have CH3, CH2, then I have carbon here, which connects with the hydrogen, which connects with the hydrogen. I have the chloride here. I'm just going to react it with what? Let's say, for example, it's not necessarily going to equilibrium. I'm just going to say that it's going to come with the reactivity with, let's say, for example, sodium methoxide. We do not care about the naming. Don't be frightened. From next session, we are just going to show what they are. But at this stage, I'm just going to show you just as a demonstration, okay? That how the things work. So you do not need to just go so much into the details. What is the sodium methoxide? Why do I call it like that way? Don't worry. From next week, you're going to see more in details. Now I'm just going to show you how to walk through this. Listen, when we come with these kind of figures from next week, all the things that we have to care is that we are looking for reactivity. We want to see some excitement in the structures that we have. We just want to communicate with this. Now, we remember the first thing to do as what we learned before we just went for the break, we have to see that either we can communicate with the structures that I have here, which is the structures that we built before. Now, you remember from the functional groups that we discussed on the chart, we had alkyl halides. And we learned that, for example, from there, the halides, which is the halogens, the elements from the 7 group of the periodic table, which are fluorine, chlorine, bromine, iodine, they are actually representing a functional groups. Huh? Now, that's what I see. Then the first step is that I see that I can talk and communicate with this structure because there's an element there as a functional group. Otherwise, if I couldn't see an element, I couldn't do much. It becomes more complex than what we are doing in this semester. Now, as long as there is a chloride here, then I know that, okay, I find the right person in the subway to talk with. That's the chloride. Now, I approach to talk with him. Now, the thing is that you're going to see the key, the golden key for all the things that we are going to do from next week all the way to week 15, particularly when we just reach for the final exam, is that we have to start the reaction. For example, if you see someone next to yourself, you want to talk with them. How do you start communicating with them? You say hi. In order to say hi in organic chemistry is this. You have to find a lone pair of the electrons that they are not confined in resonance structures, the one that you learned from chemistry 1, that you can move it around. That's how you can create new structures, new chemical compounds. Then the key is that thing. Then when I see there is someone that I can talk with, because there's a functional group in there, then I have to start by finding a lone pair that I can move it around. And the thing which I said right now, it becomes something that we come back again next week, all the way to week 15. And if you learn how to do with this, I guarantee if you even do, let's say, work with the drug design, with organic chemistry, more complex stuff, it's going to be much easier for you because you know how to start the reactivity. Now, I go back to this one. Then what I'm looking for is a lone pair, means 2 electrons. They are not part of the hybrid resonance structures that you cannot move it around. I'm going to go for this. Do I see an electron there? Anybody can see an electron there? See, how can I possibly see an electron? No, you do not see that. Huh? Then you see that this is the problem. I do not see an electron. Then the trick that we're going to do all the way to week 15 is that we are just going to learn the art, how to break the ice to convert it to talk with someone. And that becomes how to find the lone person. Now, I look at this one. We see that one of the key structures and characteristics of the alkyl halide is that the halogen group is there. Now, I'm going to go back with the general chemistry that you learned in the previous semesters. When we talk about group 7, you remember we talked about a very key concept, which it was electronegativity. What did it mean? Means electronegativity. It was an intrinsic property of an element. By intrinsic property, I mean something that they are born with it. For example, if your eye color is blue, that's your intrinsic property because you were born with it. And intrinsic properties for elements, this is something that they are the nature of those elements. Electronegativity is something that they are born with it. And it means the propensity of that element to grab the electrons. And now means that they are have more hunger for the electrons. You remember the trend we said in the periodic table, as you move from the lower left to the upper right, the electronegativity increases. Means that when you end up to group 7, they are extremely electronegative. Means that they are become so hungry of the electrons. They see anywhere electrons, they grab it. They have so much hunger for the electrons. Then now you see the chloride is there, which is a part of the group 7. Then you see that if you see a chloride, you should be careful. You do not share your food with it because it takes everything. Now, it means that if the food that I'm talking about, look at this line which I have there. I'm just going to change the color for it. Look at this straight line. You remember in chemistry, this straight line in the Lewis structure is not a line. It represents 2 electrons. Remember, it's not a simple line you draw from here to there. It's a symbol to represent there are 2 electrons there, but they are shared. Then when I look at this one, I see 2 electrons, one from here, 1 electron here. Now, the unfortunate thing or the fortunate thing is that these lone pairs, for example, look at that. This one is going to be you. This carbon is you. Don't fall asleep. You are there. This carbon is you. This chloride is you that now you're sitting separate. You are sharing the breakfast. You have a breakfast from teams you're sharing. He is more hungry. He's chlorine. He takes your coffee. And what do you do? He's texting. He doesn't understand what you're talking about. What did what did he do, brother? Is that you are grabbing the coffee from him. What does it mean? He's more hungry, and look at that, how muscle he has built so much muscle. He's more stronger. He's gonna grabbing all your breakfast. By doing this, I mean that look at the arrow which I'm showing. And this is very important to know how to show the arrows. It means that he's stronger, he has more muscles, he grabs all your muffin and the coffee together by this arrow. What does it mean? It means that he takes the muffin and coffee with him, takes the electron. What you end up with is that now he has one more coffee because he took yours. Then it means that the chlorine, which is him, comes with one more coffee. Previously, he had 7 electrons. Now he gets 8 electrons. 8 minus 7 becomes how much? No, becomes, look at that. Now you have 8 electrons there. You had 7 before. You have one more electron, means that you get one negative charge there. Because 1 electron, 1 coffee more he has. Now, on the other hand, look at that. What I'm going to do next is this. What happens to you between you and you? Now you are not friends anymore because you took your coffee. And what happens between you? You end up with this. You have CH3, CH2, C. I have hydrogen there. I have hydrogen there. And now you're crying. Now, look at this. There is no coffee. The Cl, there is no coffee with you. And now I have to stop. And that's the most important lesson that I'm just going to give you. It's going to be used for all the next sessions that we have. And please listen to this. I did this one. I dissociated the bond. Please mute me. Okay? Jill? Adita. Please mute Adita. Mute yourself, please. I think he loved your coffee. Now, This is the most important part of the lecture. Now, at this stage, remember, from next week, this is a golden rule. The first golden rule that we learned was that we have to find a functional group to see who we talk to. Second, we have the second golden rule is that we find and identify a lone pairs of the electron that is not confined. We did it. The third is that we go for fishing. Have you done fishing? You go to a lake, do the fishing. Look, I'm going to do right now. This is a three golden rule, and this is important. For every structure, if you do this correctly, every structure, you get it right. Look at that. This is the most important one of the lecture. After that, they finish the session. And we continue with that next week. Look at that. It is me. Look at, she's crying because he took all, oh my God, the texting is so important. He took all the coffee. Now she's crying. I just come close to her to console her. Look at that, it's me. It's me here, and you're crying now. What I'm gonna do right now is that I put my hands in my pocket. I draw a fishing net, and I draw that fishing net around here. Okay? You see, the net crosses these lines in between. Now, I have to ask myself two questions. The first question is that I look at the carbon which I'm standing on, and I ask myself, oh my God, what is the address? Adita, please mute myself. Now you're mute. Now, I ask myself the first question, where am I standing on? I'm standing on the carbon. What is the address of the carbon? It's not like that's like, for example, 27 Young Street. It's not like that. The address of the elements is where they are in the periodic table. Which groups they are? Carbon is group what? Group 4. I'm going to write group 4. Everyone listen it very carefully. If you learn this one, there are few sessions left, you are mastering all the reaction. Now, this is number 4, because the address is from group 4. The second question which I ask is that how many fish I have in my net. By fish, I mean the electrons. Look at the net which I have there. How many electrons is it there? I have one here, and one. How many total? 3. I subtract them, becomes +1. And this +1 which I got over there, it means that this becomes the effective charge of the element's carbon. It means that if you're crying because somebody took your coffee, your charge is plus. I give you a plus sign. Don't cry. You have a positive sign. And this very story, this simple story that we mentioned, it is the golden key number 3. We are using it in every reaction that you build. You're going to see that from next week, some of the pathways, you are building one reaction upon the other one. Then at every step, you have to stop, find the effective charge, a formal charge, then move on. If your formal charge is wrong, or if you do not find it correctly, everything goes in a different direction and becomes wrong. Then this golden rule, which we call that the fishing rule, you draw a fishing net around an element to find the effective charge, becomes an incredibly important and powerful rule. Okay? Now, we created this one. You see the carbon gets a positive charge. Next week, we see that, we call that carbocation or electrofield. Next week, I'm just going to expand more on it, and we're just going to see. Then I'm just going to wrap up the session by these very 3 important things that we learned, which becomes the 3 golden keys from next week. First, you identified the importance of the functional groups. Second, you identified the need to find a lone pairs at least in order to initiate your reactivity. Third, we just got what? The fishing rule to find the formal charge. Now, and that's essentially, it brings us to the end of the session. Next week, we just build on it. We talk about the nucleophilic substitution reaction, and I incorporate the concepts of the basicity and acidity from the Lewis perspective, then we should be fine then. Then any questions? No? Then I'm just gonna